I have some examples here of different sequences. The first one is just 1, 2, 3, 4, 5. It's just the sequence of the first 5 integers. And it has a last term, so that would be an example of a finite sequence. The second one here is 1, 4, 9, 16. And if you recognize those numbers, those are perfect square numbers. So it's a sequence of the perfect square starting at 1. And the dot, dot, dot at the end, that's what we call the ellipsis, which I've been talking about. It indicates that the sequence continues indefinitely, so it's an infinite sequence. The third one I have here all have fractions, and it's 1/2, then 1/3, 1/4, 1/5, 1/6. If you were making a prediction, if there was a sixth one on a sixth term in this sequence, it would be 1/7. The next one would be 1/8. This one is finite because I don't have the ellipsis at the ends of it. So the sequence with fractions where the denominators are the integers from 2. Now, in terms of coming up with some formulas, we'll talk about that in a moment. So down here we've got formulas and notation. We use the following letters and notation to represent information about the sequence. So the n, that's like your x, it's the term number. The term number n must be a natural number. You cannot use decimal values. It's just first term, second, third, fourth, and so on. So it's just our natural numbers. Our t with a subscript n is talking about like the y value given that particular term number. So term 1, the tn represents the value, the actual term's value for the nth term in the sequence. It's sometimes written as tn, which looks more like our function notation. More commonly, though, you'll see it as written as a subscript n. So for example, in the sequence 1, 4, 7, 10, the 7 is your third term, so that we can say that T3 is equal to 7, or term 3 equals 7. Notice that the subscript of the 3 indicates it's the third term. So just make sure that you understand that information. We can use this notation to define formulas for sequences based on the value of n. All right, so if we look up above here at these examples, the actual term number is the actual value of the term as well. So a general term for this first one, I could say that term n is just equal to whatever number, term number we are working with. It's just equal to n itself. So term 1 is equal to 1, term 2 equals 2, term 3 equals 3, and so on. The next one, it's the squares. So term 1 really is 1 squared, term 2 is 2 squared, term 3 is 3 squared, term 4 is 4 squared. So my term n, the nth term, would just be taking my n, my value, the position number, and then squaring that value. So there would be a general format for that particular sequence. For the last one here, my fractions all had 1 on the top. My nth term would have a 1 on the top, and then on the bottom of that, I'm really just taking my position number, which is 1, and adding 1 to it. So this first term is 1/2. The denominator is just 1 plus 1. The third term is 1/4. If I take 3 and add 1 to it, I get the 4. The 1, 2, 3, 4, the fifth term here, on the bottom we actually have 6. It's just taking the 5 and adding 1. So on the bottom, the denominator is just my term's position plus 1. So those are my general terms for those particular examples I have up here. So for question 2 here, it says complete the table for the following sequences. So I have the sequences, and then I have some blanks for you to predict what the next terms are. A description, recursive formula, and general formula. So I'm going to do this first one here. I'm going from 1 to 4, and then from 4 to 7, 7 to 3, 7 to 10, and then 10 to 13. It looks like I'm adding 3 every time to my term to get to the next term. So if I add 3 to 13, I should get 16. Add 3 again, 16, 17, 18, 19. Add 3, 20, 21, 22. Add 3, 23, 24, 25. So the pattern description is that we're just adding 3 to the previous term. All right, so sometimes like in the above examples we were squaring the term numbers or doing some other things to it, so it's not just a plain old adding. This one, because we are just adding a value every time, it is an arithmetic sequence, which goes with linear relationships here. Previous, and I'm having trouble spelling previous. So add 3 to the previous term. So as a recursive formula, I'm going to specify a seed. My term 1 is equal to 1. And then any other term, my nth term, I would take the term that was before it, which is term n take away 1, and then I'm adding 3 to that value. So that's my recursive formula. My general formula, I would have a plus 3 as my slope. It's a linear relationship. The plus 3 represents our slope. So my term n would be 3 times the n value. And when n was 1, my answer was actually equal to 1. So I would have 3 times 1, that would give me 3, but I don't want 3, I actually want 1. I would have to take 2 away from that. Okay, or if you think of a table of values, in terms of an x and a y, we have a 1 and a 1, and a 2 has a value of 4. If I work backwards, I'm really finding the y-intercept. I need to think backwards, and I would have to subtract 3 from that 1 to get back to have a y-intercept of negative 2 there. Okay, so just different ways of thinking of that. Try the next ones, put this video on pause, try the next ones, and then you can press play and see what you've gotten compared to what I got. Okay, I've written descriptions for the next 4 examples that we have here on the chart. Now, some of these are easy to do as both a recursive and as a general term. Some only make sense to do a recursive, and some only make sense to do a general term for them. So we'll talk about each of these. I'm doubling the previous term, so if I keep going with this pattern, if I double 32, I get 64. Double 64, I get 128, then 256, and 512 should go here. So doubling the previous term, in terms of a recursive formula, I need to set a seed first of all. So term 1 is defined to be equal to V4, and then term n is the previous term, just doubled, so times the previous term by 2, or 2 times tn take away 1. Now, in terms of what we know, these are all just multiples of 2. So when we multiply or have a common ratio, we're really looking at an exponential function here, just what we had finished with up before Christmas time, our Christmas break. So if you look at 4 really is 2 squared. 8 is really 2 cubed. 16 is 2 to the 4, and so on. So my nth term, term n, would be equal to 2 to the exponent of n plus 1 more, because the first term was really 2 to the exponent of 2, not 2 to the exponent of 1. My second term was 2 to the 3, so my second term, n is 2, 2 plus 1 is the 3, and so on. The next one are our cubed numbers, so 1 cubed is 1, 2 cubed, so this is 1 cubed here, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and so on. 6 cubed, 7 cubed, 8 cubed would be whatever answers you get would go into those next 3 blanks there. In terms of recursive, those are all really independent. It's not like I'm just doing something to the previous value to figure out the next one. So I'm not going to write a recursive because it doesn't really make sense for that one. For this one, it's just taking the value of the term's position and cubing it. A very simple general formula. Likewise for our next one here, the top number is just going up by 1, so the next one should be a 5. The bottom number is a multiple of 3, so 3 to the 1 is this 3, this is 3 squared, this is 3 cubed, this is 3 to the 4, this would be 3 to the 5, which I believe is 243, and I only remember that because that's our classroom number. So again, our general term is fairly straightforward. It's just the term's position on the top, the n is on the top, and then we would have 3 to the exponent of n on the bottom. Again, I'm not going to bother with a recursive formula for that because it's not super easy to do. I have come up with one in the past and I forget what it was, but it did take me a long time to come up with it. So don't panic about that one if you didn't get that. And so on with our sequence there. Now this last one, it's really kind of crazy because mathematically what's happening here is if I took these first two terms here and add them together, I get the 2. And then if I take 1 plus 2, it gives me the 3. And then 2 plus 3 gives me the 5. 3 plus 5 gives me the 8. So this one is just taking the previous two terms and adding them together to get the next term. This one, it is not very easy to come up with a general formula for it, if it's even possible. I don't know that it is possible. I can't remember whether I was able to get that one to work out or not. So in terms of coming up with my next three blanks here, I would take my 13 and 21. If I add those together, I get 34. So 34 would go in that blank. 21 plus 34 should be a 55, I believe. And then add 34 and 55, that gives you 89, I think, for this last blank. Correct it if it's incorrect. For this one, because I need two original values to start with, I'm going to have to set two seeds to this. I have to do two values here. Term 1 is equal to 1, and term 2 is also equal to 1. So once I have my two values together here, my term n is just taking the term that was 2 below it, so term n take away 2, and adding to it the term that's right next to it, which is n minus 1, right before it. So that's its recursive formula there. All right, try the next page of questions, see how you do, and then you can check your work on that.